Welcome to a screencast introducing limit notation to describe local behavior. In this video, we will quickly review what we previously learned about limit notation and using it to express long-range behavior. Then we will use limit notation to describe the local behavior of a function. Recall, the notation, the limit of f of t as t increases without bound equals L, or the limit of f of t as t decreases without bound equals L, means that we can make the value of f of t as close to the number L as we'd like by letting t be sufficiently large or sufficiently small. The value of f eventually stops changing much and tends toward a single value, and this value means that y equals L is a horizontal asymptote of the function f. We previously looked at f of x equals e to the x and observed that the limit of e to the x as x decreases without bound equals 0, meaning we can make e to the x as close to 0 as we'd like by making x sufficiently small, and we thus concluded that y equals 0 is a horizontal asymptote of y equals e to the x. Similarly, we observed that the limit of 2 minus 3e raised to the negative x as x increases without bound equals 2. And since we can make 2 minus 3e to the negative x as close to the value 2 as we want by making x sufficiently large, we concluded that y equals 2 is a horizontal asymptote. We can use limit notation in related natural ways to express other patterns we see in function behavior. Specifically, we're interested in thinking about input values approaching a particular value at which the function is not defined. For example, consider this graph of f of t equals the natural log of t. We know the natural logarithm function is not defined at t equals 0, and that as t approaches 0, the outputs of the natural log of t decrease without bound. We can write this in limit notation as the limit of the natural log of t as t tends towards 0 equals negative infinity. In general, if the value of f of t decreases without bound as t approaches a specific value a, we write the limit of f of t as t approaches a equals negative infinity. Or consider the graph of f of t equals 1 over t squared. We know 1 over t squared is undefined at t equals 0, because that would make the denominator 0, and we observe that as t approaches 0, the outputs of 1 over t squared increase without bound. We can write this in limit notation as the limit of 1 over t squared as t approaches 0 equals infinity. In general, if the value of f of t increases without bound as t approaches a specific value a, then we write the limit of f of t as t approaches a equals infinity. Sometimes the outputs of a function increase on one side of an input value and decrease on the other side of the input value. In that case, we need a special notation. So, if t approaches a from the left, we write the limit of f of t as t approaches a, and we use this little negative sign in the exponent. And if t approaches a from the right, then we write the limit of f of t as t approaches a, and we use this plus sign in the exponent. So for example, consider the function h of t equals the tangent of t. As t approaches pi over 2 from the left, the outputs of the tangent of t increase without bound. So we would write this as the limit of the tangent of t as t tends towards pi over 2 from the left equals infinity. Notice that negative in the exponent signifying from the left. And as t approaches pi over 2 from the right, the outputs of the tangent of t decrease without bound, which we can write as the limit of the tangent of t as x approaches pi over 2 from the right equals negative infinity. Notice that plus sign in the exponent signifying t is approaching pi over 2 from the right. In the previous examples, we looked at the behavior of the functions at a specific input value. That is, we used limit notation to describe the function's local behavior. You may have also noticed that every function had a vertical asymptote at the specific input value. In fact, if the limit of f of x as x approaches a from the left equals infinity, or the limit of f of x as x approaches a from the right equals infinity, or alternatively, if the limit of f of x as x approaches a from the left equals negative infinity, or the limit of f of x as x approaches a from the right equals negative infinity, then f will have a vertical asymptote at x equals a. Since the limit of the natural log of t as t approached 0 from the right equaled negative infinity, we can say that the natural log of t has a vertical asymptote at t equals 0. Similarly, since the limit of the tangent of t as t approached pi over 2 from the left equaled infinity, and the limit of tangent of t as t approached pi over 2 from the right equaled negative infinity, we can conclude that the tangent of t has a vertical asymptote at t equals pi over 2.